Hello guys, today in this video we are going to discuss about the relationship between minority carrier electron concentration in p region. Okay, minority carrier electron concentration in p region at the junction to the majority carrier electron concentration in the n region of the junction of a p-n junction in thermal equilibrium, or in other words you can also say the boundary condition. Okay, the boundary condition for the flow of charge carriers, for the flow of charge carriers. Okay, so in this particular video we are going to find the relationship between the minority carrier electron concentration in p region. That means in p region electron will be considered as the minority carrier, so we need to find out what is that relationship between the electron in both p region and n region. In p region the electron concentration is said to be minority carrier concentration, and in n region the electron will be the majority carrier concentration. So in a p-n junction, when the charge flows from n region to p region or p region to n region, what is that relationship between these majority carrier electron concentration and the minority carrier electron concentration, or the majority carrier concentration of holes, okay, hole concentration, or the minority carrier hole concentration. So that is what we are going to discuss today. Okay, and using this we can further understand in a better way how these minority charge carriers or the majority charge carriers they flow from p region to n region or n region to p region. Okay, so let us start with that. When we said suppose I will just show you the p region. Okay, let us take the p region. When I said p type semiconductor, of course it's a extrinsic it's an extrinsic semiconductor, right? So in that extrinsic semiconductor or p type semiconductor, if you will draw the conduction band, this is the conduction band, you can see the valence band we have, and then we said trivalent impurity atoms were added so that acceptor energy level is created, right? So at any temperature greater than 0 Kelvin, or let us take T is 300 Kelvin, which is considered to be the room temperature here. So in this, at this particular temperature, room temperature T is equal to 300 Kelvin, we already have some electrons in the conduction band and some holes in the valence band, right? And these are the intrinsic electrons and intrinsic holes that is there in the conduction band and valence band at T is equal to 300 Kelvin or room temperature. Okay, so because of thermal agitation, few of the electrons were elevated from the valence band to the conduction band. In addition to this, as we said, there are acceptor atoms over here in the acceptor energy level. Electrons, okay, can also be elevated from the valence band to that acceptor state. Acceptor state can accept one electron. So because of this, there will be extra holes created over here, and we said there will be negative immobile ions here. Okay, these are negative immobile and fixed ions that we got, right? And corresponding values or corresponding number of holes you will be able to see. Okay, so these are all the holes that is created in the valence band because of because of elevation of electrons from the valence band to this acceptor state. So in a complete ionization case, complete ionization means when all the acceptor atoms will receive one electron from the valence band, the whole acceptor impurity atom is completely ionized. Okay, so that is what is called complete ionization. So in this case you can see that you have some amount of Ni over here, sorry, I mean Ni, intrinsic carrier concentration. Okay, or you write Pi, Ni is equal to Pi, so that's why I just, okay, let me just write Pi over here, and this is your Ni, intrinsic carrier concentration. And then you got like here extra amount of holes. And what is that extra amount of holes? Whatever impurity here you took, like Na is the concentration of impurity atoms that we added per centimeter cube. So if this number is Na, right, the total impurity here you can see this, these ionized atoms are Na minus, then you can say that okay, na amount of holes are created over here, because every acceptor atom is accepting one electron, right? So the total number of holes already we have discussed here. So total number of holes will be here na plus pi, okay, or this intrinsic carrier concentration, right? But the number of electrons is here like ni as it is. Understood? Now this na minus is the immobile or the fixed ions that we got. Okay, so now these things we will write in a different notation so that it will enhance our understanding of this majority and minority charge carrier distribution in the bulk material, in this bulk material that is shown in the diagram. Okay, so what I'm going to write is, suppose this is our p region. So in the p region, what we got, there are few electrons present. So there are few electrons, you can see here, intrinsic carrier concentration that will be there. So few electrons are there. The majority charge carrier, you can see the number of holes over here. So there will be holes here. So let me just put those holes, like these are the holes. Okay, more number of holes. Okay, the positive charge carriers here, these are the holes over here, right? So what we are going to write is these electron concentration. I will write electron concentration as n, as we always write. Okay, and if this electron concentration we are writing in the p region, then I will write the region here as p. So n gives you the electron concentration, p gives you the region. Okay, and then I can put a 0 here, which indicates thermal equilibrium. So if I write np0, this particular notation gives me what? So electron concentration in the p region. So electron is the minority here, you can see small number of electrons are there. So that will be treated as the minority carrier electron concentration. So if I'm writing np0, I will write this as what? This is actually minority carrier electron concentration in p region. P we can see. So in p region, in thermal equilibrium, this 0 always gives you thermal equilibrium. So in thermal equilibrium, we can write this notation this way, equilibrium. Okay, so np0 we wrote, right? Similarly, if you want to write it for the holes, over here, these holes, then we can write the same way. What I will write for the holes is concentration of hole given by p in the p region. So p and 0 is the thermal equilibrium. So what do we write? P in p region, like what do you mean by this? Holes in the p region are always the majority carrier concentration. So I will write it as majority carrier hole concentration in p region in thermal equilibrium. So these are the notations we wrote for for the p region. So np0 and pp0. The same way, if you will see the n type semiconductor. Okay, so n type semiconductor, what do we have? N type semiconductor, let me just draw the bulk material as this is our n type material. Now if you will see the energy band diagram, we have the conduction band, we have the valence band, then you doped with pentavalent impurity, so you created a donor energy level here, which I will say ed. So nd is the donor concentration per unit volume you added. So initially there were some holes already there, like there were holes and few holes in the valence band and few electrons in the conduction band already there, because you consider the temperature to be around 300 Kelvin room temperature. So thermal agitation will produce this intrinsic carrier concentration. Then you doped it. So doped it, you got donor electrons over here. These donor electrons, because of thermal agitation, will be elevated to the conduction band because the gap between ec and ed is very less. So you got extra electrons here, donor electrons, which are now elevated to the conduction band. And here what you got? Electron is lost, so you got positive immobile ions. Okay, these circles I'm putting, these are positive immobile ions created over here in the donor energy level. The same thing can also be shown here in the n type. So what do we got? The n type majority charge carriers are the electrons. So more number of electrons are here. These are the majority charge carriers in the n region. Then the minority charge carriers will be, of course, these holes present in the valence band. Number is very less. So we wrote these are the minority hole concentration. So the similar way we can write the notations, our notations. So first thing is the electron concentration n in the n region, so nn, and then 0 for thermal equilibrium. So I will write this to be what? Majority carrier electron concentration in n region in thermal equilibrium. You can see 0 here, so thermal equilibrium, in thermal equilibrium. So there should be no confusion in the notations used. N is majority. N means majority because electron in the N region is always the majority charge carrier. So majority carrier electron concentration in N region in thermal equilibrium. Right. The same way, if you want to write the holes here, hole concentration, we will write P for concentration of holes in N region. In the N type semiconductor you're writing, so you write the region, that is N, and 0 thermal equilibrium. So P is the minority carrier concentration, of course. So I will write it as minority carrier hole concentration in n region in thermal equilibrium, in thermal equilibrium. So these are the notations we use. Right now we will use these notations, okay, in a PN junction taken together, okay, and we'll try to establish a relationship between the majority concentration and the minority concentration in the opposite regions. So what do you mean by this? When I said this, now let me just show you the bulk material, that is our PN junction. Okay, so you have the metallurgical junction. For example, this is the metallurgical junction. You have the abrupt boundaries. So this is the space charge region we said, okay, and this is P region, N region. Space charge width, you can consider this to be xn, and this is minus xp, as you have already discussed. Now I will just use the notations. Okay, so in the P region, if I wanted to show you what are the charge carriers, so majority charge carriers will be the holes. So concentration of holes in the P region in thermal equilibrium, this is what we said. So this will be the majority carrier hole concentration in the P region. In addition to this, what will be there? I said there will be few electron concentration in the P region as well, because those are the intrinsic charge carriers, intrinsic carriers, which is already there in the conduction band because of the temperature value. Okay, at T is equal to 300 Kelvin. So that I can write as N concentration of electron in the P region in thermal equilibrium. So the same way, the majority carrier here in the N region will be N0, electron concentration in N region in thermal equilibrium. Similarly, you can write the hole concentration will be there. So hole concentration P, okay, in the N region in thermal equilibrium. Right. So these are the actually, respective P and N region, these are the charge carriers present. Now, when we combined these P and N junction, you can see this dotted line as the metallurgical junction. We said the majority charge carrier, because the concentration of electron is more here, you can see this, okay, and the concentration of holes, hole is more there in the P region. So what will happen? Diffusion will occur, right? So diffusion will occur, and then space charge region is created to maintain the thermal equilibrium. This is what we said. Okay, so this is what will happen. So the N region contains more electrons in the conduction band than the P region. Okay, the built-in potential barrier that we discussed will prevent this large density of electrons from flowing into the P region, right? So that is what we have already discussed. So once you got few of the electrons diffused from the N region, okay, here you got the space charge region here. So we said, because the nn0, okay, these carriers, okay, they move from the N region to this region, to this P region, right? So that will give us what? The positive space charge region here. Similarly, some holes like here pp0, the majority charge carriers, they will start moving from P to N region, and hence that will create a negative space charge region. Remember, these negative space charge region, these are space charge, Okay, so they are not actually producing any current over here. Okay, drip current, they are just fixed immobile, charge over here, though they produce a electric field. So the induced electric field here we have already determined. So what you got, you got few amount of n0 already, okay, moved, diffused from n region to p region. So this is the new charge. I am just, so this is the new charge carrier you got because of the diffusion of electrons from n region to p region. Same way here also you can see few amounts of pp0, okay, which is diffused from the p region to the n region, that we will see. Okay, after this no further flow of nn0 to this region, p region is allowed, and no further flow of pp0 from the p region to this is allowed. Because of what? Because of the electric field that is set over here, that is created over here, because of this electric field created over here. So this electric field now for oppose or will maintain the balance, right? And that's why we said it is equilibrium, right? It maintains the equilibrium, this induced field over here, right? Okay, so now we are going to see these charge distributions, and we are going to find a relationship between what? Between the minority electron concentration in p region, minority when I said electron concentration in p region np0, and the majority carrier concentration, okay, in the n region nn0. So we are going to establish a relationship between np0 and nn0. The similar way you can write the relation between what? P0, okay, the majority carrier hole concentration, and Pn0. Okay, so these boundary conditions we will use further in some other, like, concepts, okay, where we will find out the exact value of the current. Okay, so anyway, so now how we will do that, how we will establish a relation between these variables or these parameters. Okay, so that is what we are going to do today. Fine. So let us start with a simple expression that we have already obtained, which is known as the built-in potential barrier. So we said there will be a potential barrier created in this space charge region, in this particular space charge region, which we have already derived, and it was VBI, V for potential, BI for built-in I'm writing. So this we have already derived. You can refer to the previous video that we have derived or discussed. Okay, this was given by NAND divided by NI square. Okay, this was the expression that we have derived. Okay, so further simplifying, we can write, like, this is VBI take KT by E over here. That gives you ln NAND logarithm of NAND by NI square, right? So I can further, like, this E will go up, and then take EVBI divided by KT, and then just take the exponential of e to the power this, e to the power of this whole thing can now be written as NAND by NI square, right? So from this I can write NI square divided by NAND, just taking the reciprocal of this, e to the power minus exponential of minus e to the power minus EVBI divided by KT, right? So this is what we got, Ni square, okay, from the built-in potential barrier expression from this, right? So now we will use our notations means what? This pp0, the majority carrier hole concentration in p region, np0, the minority carrier electron concentration in p region. Similarly here, majority charge carrier electron concentration in n region, minority carrier hole concentration in the n region. So we are going to use these these notations to write. Okay, now if you'll see in the extrinsic semiconductor, this is the majority in the p region. If you see, pp0 is the majority, np0 is the minority or the electron concentration. This is the whole concentration. So using the law of mass action, we know that for p region we can write nn0 multiplied with pn0, okay, Pn0 for the n region. Sorry, I'm writing it for the n region. Okay, Pn0 and Nn0. Or else you can write for p region, you can write like Pp0 and Np0, right? So for the extrinsic semiconductor, the law of mass action is followed. So you can write Nn0 Pn0, that is the product of the concentration of electrons and the concentration of holes in n region in thermal equilibrium, right? That must be an I square, right? Okay, so this is known. And similarly, for the p region, both are in p region. One is the majority, the other is the minority, or the whole concentration multiplied with the electron concentration. This will also give us Ni square. So we are going to use this, okay, and modify whatever we got, we obtained over here. Ni square by Na Nd is equal to exponential to the power minus e vvi by kt. Okay, so how we will do that? Now, one thing we will see, we will consider the complete ionization case. So if you remember, I showed you just in the other slide, I told you what is complete ionization here. Complete ionization, you can see Nd minus, okay, amount you got, this is your Nd, you got Nd number of electrons, extra electrons you got, right? And this intrinsic carrier concentration is very less. Okay, so we said this is very very less, and this is Ni. So now if somebody will ask me, this is for n type we have written. So for n type, what is the majority carrier electron concentration in the conduction band? I can say this is nearly equal to Nd, because I just ignored this Ni value as compared to this capital Nd. Okay, ideally it is actually equal to what? Equal to Nd plus Ni, right? But this Ni value is very very less as compared to this Nd when you are considering the complete ionization at T is equal to 300 Kelvin or room temperature. So in that case, I can write Nn0 is nearly equal to what? This capital Nd, ignoring the Ni value or the intrinsic carrier concentration, which is very less in number. Okay, you understood? So this way, here also you can see, we said here also you got Na number of holes here, right? For complete ionization, all the acceptor atoms actually accepted one electron, so holes were created in the valence band. So you got this Na. Now if you write the total hole concentration in the p region, so hole concentration means p, in the p region is this, thermal equilibrium means pp0. So this pp0 can also be written as what? Actually Na plus Ni or Pi, whatever you said. Ni is equal to Pi because intrinsic carrier concentration. So if this Pi is very small, as you can see, the number of Pi or the intrinsic carrier concentration is less, so we can write this Pp0 is nearly equal to our Na. Okay, so these are the values we are going to use here, okay, here in this expression. Understood? So what I will write for Na, for Na we are going to substitute what? For Na we are going to substitute, as I said, Pp0, that is the whole concentration in the P region, right? And for Nd we are going to substitute what? Nn0. Okay, just substitute this and rewrite the equation. Okay, then what will happen? So let me just write this way. So what we said, considering complete ionization, okay, we said Nn0 is nearly equal to Nd, and P0, that is the majority whole concentration in P region, is nearly equal to Na. Okay, so now for P region, if I write P region, what we can write is Np0 multiplied with Pp0, law of mass action, that is Ni square, intrinsic carrier concentration, square of intrinsic carrier concentration. Okay, so now this we can write Np0 is equal to Ni square divided by Pp0, which you can write as Ni square, and our Pp0 we consider to be Na, so divided by Na, right? Or else you can substitute Na further is equal to Ni square divided by Np0. Okay, so in place of Na we can write this. Okay, now similarly you can substitute the values, as I said. Nd is equal to your nn0 here, nd is equal to nn0, and you substitute Na is ni square by np0. Okay, in the above equation, the equation that we wrote. So let me just rewrite it again so that I can substitute Na as ni square divided by np0 and nn0 as nd. Okay, so these are the two values that we will substitute in that equation that we obtained from VVI, from the expression of VVI. So our original expression, I'm just writing it again, Ni square divided by NaNd is equal to e to the power, okay, minus EVBI divided by KT, right? Now what I said, we will substitute for this Na and Nd. Okay, so we can write this Ni square, and this Na we wrote as Ni square divided by Np0 multiplied with Nn0, right? That can be written as exponential of the rest, EVBI divided by KT, right? So from this you can see whatever got cancelled, Ni square got cancelled, this Np0 will go up. So we got this way. So we got Np0 divided by Nn0 is equal to exponential of minus EVBI divided by KT, right? Okay, or else you can write it as Np0 is equal to Nn0 exponential of e to the power minus EVBI divided by KT. This way you can write. The same way you can also write, like, Nd you substitute as you substitute for a Nd as Ni square. What do we said? Okay, I'll do it. So for if you will do the just opposite, like, you wrote Na as, Ni square divided by Np0. Okay, now you can substitute for Nd as well. You can start for the N region. Okay, I'm just doing it again. So fine, we got this for the P region. Np0 equals to Nn0 exponential of minus EVBI by KT. So Nn0 is what? The electron concentration, majority electron concentration in the N region, you can see, right, in thermal equilibrium. Okay, multiplied with e to the power minus EVBI divided by KT. So these are all known variables. If you substitute these values, then you can find out what is the electron concentration, minority carrier electron concentration in the P region. So that's why the heading we said that we are going to find out what the relationship between minority carrier electron concentration in P region, minority carrier electron concentration in P region, electron concentration. So we wrote N in P region, this Np, and in thermal equilibrium 0 with what? In terms of what? In terms of majority carrier electron concentration, that is N in N region in thermal equilibrium. So that was our objective to establish, like, for electron concentration. Similarly, you can write it for, like, here we did it for P region, and this is N region. So we uh, could establish a relationship. Okay, here you can see. So that is what we got, Np0 and Nn0. They are related by this factor exponential minus EVBI by KT is multiplied with Nn0 to give you Np0. Okay, now come to this part. Okay, like I said, this is what we did for the P region, and we wrote Na as this, and we substituted Nd for Nn0, right? We substituted for this. The same thing can also be done for N region. Okay, so for the N region, if you'll write, for N region, if you'll write N region, if you'll write, then what is the electron concentration and what is the hole concentration? So electron concentration, majority charge carrier electron concentration in N region is 0, right? And the electron concentration and the hole concentration P, Okay, and in n region n0 you can say electron concentration, majority charge carrier electron concentration, here minority carrier hole concentration in n region, that must be equal to ni square, right? Okay, so now you substitute for this. So substitute for, like, nn0, we said nn0 is actually your nd value, and this pn0. Okay, we need to find out this pn0. nn0 we can substitute nd. Now pn0 we need to write in some other form, right? So for n region, as we said, nn0 into pn0 is ni square. Then we can write this pn0 here can be written as ni square divided by nn0, which is ni square divided by nd. Nn0 is nd. So we got this pn0, right? Now you go back to the equation, original equation, and substitute it. So we got ni square divided by nd. Okay, this is equal to exponential of minus e bbi divided by kt, right? So what I can do is ni square, we kept it as it is, and divided by, so here, sorry, nd we can write it as ni square divided by pn0, so that I can substitute over here for nd. And na we can just directly write pp0, so we can have that value pp0 for na, and nd we got ni square divided by pn0, right? So see, p this cancelled, and we have, sorry, this is equal to e to the power exponential of minus e vbi by kt, as it is we kept. So the next we can see pn0, this pn0 will go up. So we got pn0 is equal to pn0 by pp0. Next, one more, no, step you can do, exponential of minus e vbi by kt you got, and then you can just open it, like, you can write pn0 is equal to pp0 and e to the power minus e vbi by kt, e vbi by kt. So these two things we got. So pn0 gives you what, the minority hole concentration in n region is related to what, the majority hole concentration in p region, right? So this is how they are related. So these two we can finally, like, write what we got, these two equations. That was our objective. So let me just write it for n region what we got, and for p region what we got. Okay, so for n region, we got the relationship between the whole concentration as a majority charge carrier, as a minority charge carrier. So you got Pn0 is equal to Pp0 exponential of minus EVBI by KT, right? This is what we got. And for P region, we got what, np0, just opposite, you can see np0 gives you nn0 exponential of minus evbi divided by kt, right? So yeah, so this is known as the boundary condition to find out the flow of these majority charge carriers from P to N or N to P region, and we are going to use this when we will derive the equation for the current. Okay, so yeah, so this is it in this video. So we got the relationship between what, between the majority charge carrier electron concentration in n region to minority carrier electron concentration in p region, and vice versa, like the same way we can write it for the whole. Okay, thank you for watching.